This is the solution video for question 9 from paper 1 of the 2019 TMUA exam. In this question we're asked to consider two curves, y equals p root x and x equals p root y, where p is some positive constant. And we're asked to find the area enclosed between the curves. And we're given a few options for what our answer might be. We're given 7 in total. So A, 2/3 p to the 5 over 2, 4/3 p to the 5 over 2 minus p squared, p to the 4 over 6, p to the 4 over 3, 2/3 p cubed minus 1/3 p to the 4, 4/3 p cubed minus p to the 4, and finally 2p to the 4 for G. So the first step in this is to come up with some sketches of these curves, because it's very hard to work out the area when we don't really know what it looks like, and if we sketch the curves we'll have a rough idea where to go. So let's get some axes and let's start with this one. Y equals p root x. This is quite a nice easy curve to sketch because we know how what a square root graph looks like, and we're just times it by a constant which is positive, and so we get something looking like this. Now the other one's more difficult. X equals p root y. So if we make y the subject, maybe we'll have a better idea what's going on. So let's square both sides. If we square both sides and divide by p squared, we get y is equal to x squared over p squared. And we know we're in this quadrant, and we know what a normal quadratic looks like. So we know that this graph is going to look something like the right hand side of a quadratic like this, and we know it's going to pass through 0, 0 simply by subbing in x is 0, y is 0. And so the area we need to consider looks something like this, shaded in green. So given this, the thing that leaps out to do is to find the x coordinate of this, because most likely we're going to be integrating something between these limits to find this area. So we need to know what our limits are. And we know this point 0, but we don't know this point. So to find this, let's look at this, because we're using x equals p root y and then substituting y equals p root x in. So if x satisfies this, it will be on the intersection. So getting rid of some of the square roots and converting to fractional powers, we get x is equal to p to the 3 over 2 times x to the 1 over 4. Now, from here, we've got one obvious solution, x equals 0. But if x isn't 0, we can happily divide through by x to the 1 over 4 and obtain x to the 3 over 4 is equal to p to the 3 over 2. Now from here, if we raise both sides to the power of 4 over 3, hopefully we'll get x on its own. Indeed we do. So x is p to the 3 over 2 to the 4 over 3. Then we can times these powers and obtain x equals p squared. So we know the x coordinate of this intersection point is p squared. So now all that remains to do is take the function for y for the red curve minus the function for y for the orange curve, then integrate that between 0 and p squared, and that will generate the area between these curves here. So let's do that. So we've got px to the half here, and minus x squared over p squared, which is what we deduced earlier here. So integrating that up, we've got a half power here, so we have x to the 3 over 2 times 2/3, and x squared, so we get the x cubed, and then divide through by the 3 here, and our limits are, as we worked out, p squared and 0. So substituting these limits in, we get 2/3 p times p squared to the 3 over 2, minus p squared all cubed over 3p squared, minus 0, because if we shove in x equals 0 into this, we're just going to get 0 out. So now, tidying this all up a bit, p squared to the 3 over 2, well, that's just p cubed, times p here, p to the 4, then minus 1/3 p to the 4 from p to the 6 over p squared over 3. And then we get 1/3 p to the 4, and that corresponds to D in our answers, and so we know in fact, our area corresponds to answer